So we were discussing just how to get now Q dot boiler in this case. So Q dot N is equal to M dot times H1 minus H11. And just we need to get now what is H11. Okay, so if we go back to our graph, what is happening? We have a fluid that is coming from pump 2. And the mass flow rate through pump 2 is, as we said, it's the addition of X times M dot and Y times M dot. So because here we have fraction X, here we have fraction Y. So this is X plus Y. Okay. And then what is coming from the other loop here through pump 1 is the remaining fraction of the flow, which is 1 minus X minus Y. Now, what will happen in the mixing chamber is very similar to the process heater. The only difference is that in the process heater, okay, you have production of, you have heat extraction. When you mix 4 and 5, you will take a part of their energy and extract it to another fluid or liquid. So here you have, let's say, water here that will extract this energy, Q dot P. Okay, that's why the energy at the outlet will be smaller. Okay, while for your mixing chamber, you have well-insulated mixing chamber. So you don't have any lost heat to the surrounding. So if you write the energy balance for the mixing chamber, you can say that for my mixing chamber, I have Q dot minus sum of W dot is equal to a sum of M dot in HN, sum of M dot out H out, minus sum of M dot in HN. But since I have a well-insulated mixing chamber and I have no work acting on it or produced by my mixing chamber, it's like if you want a well-insulated rigid tank. Okay, so then I will say that Q dot and W dot will be equal both to 0. And I can deduce that for my mixing chamber, I have, it's like a heat exchanger. I am exchanging heat between my two flows. Okay, the flow coming from first loop and flow coming from the second loop. So all I have to do now is to write that for my mixing chamber, the inlets are 9 and 10, and the outlet is 11. And as we discussed, the mass fraction through 11 is 1. The mass fraction through 0.10 is X plus Y. And the mass fraction through 0.9 is 1 minus X minus Y. So now the energy balance for my mixing chamber will be M dot times X plus Y at 0.10, so times H10. Plus M dot times the other fraction, which is 1 minus X minus Y times H at 0.9 is equal to M dot total, so which is 1. The fraction is 1 because now I added these two fractions, so I get 1. So M dot times H11. And in this way, I can get the value of H11. Okay. Now I have everything. I have Q dot boiler. I have the amount of Q dot process heat. I have W dot net. So my utilization factor will be equal to, as we discussed, W dot net, which is W dot turbine 1 plus W dot turbine 2 minus W dot pump 1 minus W dot pump 2. And we don't forget to add the process heat that we were able to extract, because this is a useful heat. And as I told you, if I give you an efficiency for your process heater, you just have to multiply the maximum extracted heat Q dot P by the percentage that I give you. And just you multiply here by the efficiency of the process heater, okay, over Q dot N, which is at the boiler level, which is M dot times H1 minus H11, okay? And let us see together, let us compare the utilization factors for these different configurations. So we said we can have 100% process heat production, we can have 100% electricity production, and we can have mixture. We can expect the results, okay? The highest utilization factor will be for the case of 100% process heater. Why? Because in this case, the losses are minimal. You just have the losses through your pump. And this is good, but in general, we don't want, in majority of application, we care to transform heat also in electricity, because heat is already, you have it in thermal form, so you can use it directly. If you don't want to produce electricity, no need for the cycle. You can use it directly from the boiler by putting a heat exchanger at the boiler. But the idea is that I need also sometimes to produce electricity, okay? So no problem, okay? So what will happen then? You need to do cogeneration. You want to produce process heat and you want to produce electrical work, okay? So that's why we'll see that for pure electricity production, you will have the lowest value of utilization factor. And for just pure process heat, you will have the highest value of utilization factor. And whenever you produce both, which is cogeneration, you have in between, you have a value in between. And we can check this from calculations. So we can see that in the first case, if we just operate if we want to have maximum process heat, and we calculate the factors, the utilization factor will be nearly 100%, because losses and pump work are really small relative to the value of Q dot boiler, okay? And that's why you can say that it's nearly, the utilization factor will be nearly very close to 100. On the other hand, if you want to purely produce electricity, okay, then when you calculate the utilization factor, you will get around 40.8%. So you see the difference. The difference is huge. But we need to produce electricity. We need to produce work. We don't want just to have heat. Okay. So to have, like, if you want a compromise between electricity production and efficiency, we use cogeneration, which is production of several useful forms of energy as heat and work. So for the third case, where they gave us the percentages, 10% and 70%, if you do the calculation, you will find that for cogeneration, the utilization factor is 86.5%, which is great. So you are able to produce electricity while maintaining a high utilization factor, much larger than the one for pure electricity production. So this was the purpose of this problem, to show you how you can produce several forms of energy using the same cycle, and how you can control the percentages of process heat and electrical work. Thank you.